Okay, welcome. This is Algebra 1, Semester 2, Unit 5, Exponential Functions. Hopefully you guys are thinking, oh, I've kind of heard about this, and you're thinking back to last week when we did the sequences. And if you look on the sequence, I hope you're saying that would be arithmetic, because it's going by a plus 10. If we look at the factors here, they go by 10. Whoops, the first one was 0, then 10, then 20. And when you guys graph that, I know a lot of you didn't keep graphing all week, but you would have found that it was a straight line. And that's why we called it linear, because a linear function is related to arithmetic sequence. Okay? The next sequence that we looked at was geometric, and that was when it multiplied. So we have 3, and then 3 times 2 is 6, times 2 is 12, times 2 is 24. And when you plotted that one, you found that it had a curve. At the one, it started at 3, and 6, and it did this kind of a curve. Now, I hope all of you said, Ms. Kane, you did that wrong in that graph there, because you're exactly right. If you did, I shouldn't have connected it. These are disconnected because it doesn't contain all the elements in between. The term number is 1, the value is 0. The term number is 2, the value is, and I even moved it over too far, I'm sorry. It should be like that. Okay, so when the value is 2, then it's 10, 3, it's 20, but we don't have the points in between. Same thing on this one. This is our geometric, and it is a exponential function. And when we draw with the dots, then that is discrete. If you see a graph drawn with disconnected dots, it's discrete. Okay? So, a geometric sequence, remember your formula last week, a of n equals a of 1, the first term, times your rate, n minus 1, is almost the same as exponential function. I'm sorry, my ink got smeared off as I slid it across here. And the formula for it is ab to the x, and you would have a function of f of x. Okay, so you might see some similarities here. A geometric sequence is an exponential function. Exponential functions are only geometric sequences, though, if their domain is limited. I put it inside of a box that was coming in on it. Only if it's limited evenly. So if the domain is even, then it's a geometric sequence. Otherwise, it's an exponential function that's not a geometric sequence. Okay, a couple rules that you're going to want to know is, and these should be review as well, any number, as long as it's not 0, to the 0th power is equal to 1. Any value besides 0 raised to a negative is equal to that value put underneath the fraction, like so. I wanted to bring up this geometric sequence maybe to help you in understanding that. If you look at this, you can say, oh, we're multiplying by a half, multiplying by a half, multiplying by a half. Well, there's another way that I could represent that sequence. 4 is also the same thing as 2 squared. 2 is the same thing as 2 to the first. So see, I am just going down by a multiple of 2. This would be 2 to the 0th, and this is 2 to the negative 1. So right there, I've just shown you the two rules that I gave you up here. Okay, so one other thing that might help you is to remember that a over b raised to the m is the same thing as a to the m over b to the m. That's the quotient property of exponents. Okay. Now we're going to look at an actual function that they're going to have you graph. They give you the domain. So I want you to make a t-chart when you get to this kind of problem. Sorry, that should have an x up there. It's f of x 2 to the 1/3. Oh, speaking of which, well, I'll show you on the next board. Okay, so we plug in our domain values in a nice t-chart here, and I do ask that you just put the equation in the t-chart and show that it's equal to the f of x. So this would be 2 to the 1/3, negative 2. We'll work it out in a second. Negative 1, 2 to the 1/3, negative 1. 0, 2 to the 1/3 to the 0th. 2 to the 1/3 to the 1st. And 2 to the 1/3 to the 2nd. Okay, that last property is going to come into play here. The first thing we do, order of operations, would be that we don't multiply first, we raise to the exponent. So 1/3 raised to the 2nd would be 1 times 1 is 1, 3 times 3 is 9, so that becomes, oh, my pen, sorry. So that becomes 1/9 times 2. You can put the 2 over 1 if you want, but it's 2/9. Now this one raised to the first power. 1 to the first power is 1. 3 to the first power is 3. So we have 2 over 1 times 1 over 3. You just multiply straight, so it's 2 over 3. Anything to the 0th power is 1. So 2 times 1 is 2. And right here, this becomes 1 to the negative first, 3 to the negative first. Remember, with a negative exponent, you flip them. So this becomes 2 times 3 over 1, which is 6. You can put over 1 or you can just leave it that way. Now this one would be 1 to the negative second, 3 to the negative second. So it equals 2. And remember, you flip them when they're negative, so it's 3 squared is 9, 1 squared is 1, 2 times 9 is 18. So you notice here where you're multiplying by 1/3. Should look like a sequence to you. And it should be the same. Okay? So on the graph at negative 2, we go up to 18. Way up here. At negative 1, we would be at 6. At 0, we're at 1. Watch for that pattern with these. The 0 being at 1. We'll talk about why that is. Maybe you already know. Bring it in to me. At 1, it's at 2/3. And at 2, it's at 2/9. So in this case, the domain is restricted, so I won't connect it. It is a discrete function. But you could continue it. You can kind of see how it looks. And I should say only continue it in your mind because the domain wasn't continued. That is a decay function. Hopefully you spotted that when you saw that it was 1/3. But I also want you to start spotting it with the graph. Now I'll give you a hint. A growth function grows. From left to right it grows. See how the decay goes down. Okay, last little bit here. I wanted to just show you with the function, we have this rule. With our sequence last week, we had this rule. Do you see how the A's correlate? Last week, this A1 was what? Hopefully you're saying first term. And you're absolutely right. the a up here is going to be the first term. It's the value at 1. Maybe I should say. Let me think if that's correct. When x is, yeah, it's your first term. Okay, now our decay or growth factor was the r, n minus 1. And this time it's b. So now you should be able to tell me when b is greater than 1, it'd be a growth. Because that's when your factor is bigger than 1. Or when it's less than 1, it's a decay. Okay. So on this one, we'll look at what our equation would be. Well, we're going from 8 to 4. So it's 1/2. From 4 to 2, 1/2 again. And from 2 to 1, 1/2 again that we're multiplying by. So we know that our b value is 1/2 to the x. And now we want to find the y. And I'll be honest, because I'm just kind of having a brain fart right now. I'm going, man, I think I know how to find that a, but let's just make sure. We can take any of these values here. I like the 0, 1 the best, because f of x means y. We'll just plug in 1 for y. And 0 for the x. And at that point, we know that anything raised to the 0th power is 1. So 1a equals 1. That's what I was thinking is wherever 0 is, that will be your a value. Okay? So if we have a stretch or anything that way away from that, then you'd have a value here, 0, something, that'll be the a value. Okay, I'll see you in class.